A Portland Community College Mathematics Telecourse. A course in arithmetic review. Produced at Portland Community College. Basically, the division of two signed numbers follow the same rules as multiplication. That is, if I divide like signed numbers, in this case both negative, whether I write it this way with this dash meaning divided by, or whether it's written with a conventional division symbol. In algebra, this form here will more and more predominate. If we were multiplying two negatives, the answer would be positive. And so if we're dividing two negatives, the answer is positive. And then we simply divide their absolute values for the absolute value of the answer. And if we're dividing a negative number by a positive number, if we were multiplying unlike signs, two of them, the answer would be negative, and so it is with division. Then we divide the absolute values to get the absolute value of the answer. And of course, had the top been positive and the bottom been negative, the results would still be negative because I'm dividing unlike signs. Basically, that's it. Those are the rules of division right there. Now, why are the division sign rules the same as for multiplication? Well, let's look at division. If I take any number and divide it by another, I could write it this way as the top times the reciprocal of the bottom. Because you can see the top I could always write as something over 1, and if I were multiplying this back, multiplying the tops to get the new top would give me back to A, multiplying the bottoms to get the new bottom would get me back to the B. So you can see if I'm dividing these two numbers, in a sense I'm multiplying a number with its reciprocal. And if this is negative, this will be negative. So whatever rule applied for sign-wise for these two will apply for these two, because this says it's the same problem. Stating that once again then, the quotient of two like sign numbers is positive. Divide two positive, it's positive. Divide two negatives, it's positive. So, some examples. If I'm dividing two like signs, the answer is positive. Then dividing the absolute values gives me the absolute value of the answer. Again, dividing like signs, the answer is positive. Then 3 into 18 is 6. Again, you're dividing like signs, positive. Now, you have to divide fractions, but now we can only think about their absolute values. So we think 2 1/2, which is 5/2, times the reciprocal of 3/4, which is 4/3. Then in this case, recalling the cancellation law, we get 10/3, or if you wish, positive 3 1/3. The important point is this. The sign can be determined before you do the arithmetic. Then you do the arithmetic to the absolute values, which is simply another way of saying plain old-fashioned arithmetic. And the second part of our rule, the quotient of two unlike sign numbers is always negative. So if you're dividing unlike signs, the answer is negative before you even start the arithmetic. Then you simply divide the absolute values, divide the absolute values, and in this case you have an arithmetic problem of fractions once you forget your signs. Back to just plain old-fashioned arithmetic. So you have 7/8 times the reciprocal of 1/4, which is 4/1. Then recalling that we can use the cancellation law, we get our results as 7/2, or if you prefer, 3 1/2. Actually, in algebra, you will prefer this form to this form, believe it or not. But in common daily use of arithmetic, we do prefer the mixed number form, so we'll use it here. Now, please realize, going from here to here is called changing to a mixed number, not reducing. Use those facts to practice getting ready for algebra. Remember, if you have a simple equation where the variable is being multiplied by a constant, you undo the multiplication by division, in this case by 8. And that undoes that, isolating the variable, and positive divided by positive is positive 3. If you have the same kind of a problem but using signed numbers, nothing changes except your work with signed numbers. So to undo the multiplication, you still divide both sides. The division undoes the multiplication, isolating the variable, and positive into negative is negative. 5 into 35 is 7. So nothing changes except being careful when dividing or multiplying with signed numbers. Particularly in a problem like this. I am multiplying, so I'm going to undo that multiplication by division. But it is a common error for beginners to think that the multiplier is a 5. It is not. It's a negative 5. So I'm going to divide by negative 5, both sides, of course. And this undoes that, isolating the variable. Now, negative into negative is positive. 5 into 40 is 8. So be sure that when you're multiplying by a negative number, you realize that is a negative number and divide by that same negative number. Other than that precaution, the procedure is the same. Now, the other type of equation we had is when the variable is being divided by a number. And recall we undid division by multiplication. So since it's 5 doing the division, we will multiply by 5, both sides. This undoes that, isolating the m. And of course over here, 2 times 5 is 10, and we're done. Now in this problem, we do the same thing, except we must realize I'm dividing by a negative number. So I will undo that by multiplying by the same negative number. Then I have to multiply this side as well by the same negative number. So that multiplication undoes that division, isolating the variable. Now over here, a negative times a negative is positive. Of course, 2 times 3 is 6, and we're done. Let's check that. The original equation said r, which we're now claiming is positive 6, divided by negative 3 should be negative 2. And of course, a negative into a positive is negative, and 3 into 6 is 2, so it checks. So there you have it. When you're dividing like signs, the answer is always positive, and the same for multiplication. When you're dividing unlike signs, the answer is always negative, and again, the same for multiplication. Let's re-examine for a moment that process of solving equations once again. Sometimes by looking at a matter from a slightly different angle, we get more of an insight and things begin to seem more meaningful or easier. Our approach so far has been to say that we wish to isolate the variable. So we look at the variable and ask, what is the number doing to the variable? That is emphasizing the fact that it's the operation between the constant and the variable that determines what we do. The variable, the constant, is in a sense incidental. And we've been verbalizing that to undo multiplication, we divide. And incidentally, by the 5. And we further verbalize that division by 5 undoes multiplying by 5, isolating the variable, which is what we've meant by playing the game or solving the equation, to isolate the variable. But then whatever we did to undo this operation, we had to do the same thing to the number on the other side of the equation, so we had to divide it also by 5. And of course, in this case, a negative divided by a positive, unlike signs, is negative 3, which is the bulk of this lesson. Now note first, it wasn't the number we looked at, it is the operation. That's very critical to realize. See, if we had the same number 5 and the same variable m, but instead of multiplying the two, we were adding the two. To undo adding a 5, we have to subtract 5 from both sides. And of course, 5 subtract 5 is 0, isolating the m. And over here, of course, we get negative 20. So it wasn't the 5 that determined what we did. In both cases we had a 5, but we did something different. So we undid multiplying by dividing, we undid adding by subtracting from both sides. Similarly, if I had again the same variable, the same constant on both sides, but this was being subtracted, we thought to undo subtraction, we add to both sides, and incidentally, the 5. So addition undoes subtraction, isolating the m, which means we solved the equation. Then completing the arithmetic on this side, we get, in this case, of course, negative 10. Again, note how over and over in algebra we look at the operations. It's the operations that determine what we're going to do and not necessarily the numbers. That's strictly secondary to the process. But let's look at that phrase, isolating the variable, a little bit more closely. What is really meant by the phrase isolating the variable? Recall that m, or any variable, is the same thing as 1 times that variable. So we're doing more than saying m is negative 3 here. We're saying 1 times m is negative 3. There's always a 1 multiplier even when it's not written. If I were to say 2, there's always a 1 times 2 because 1 times 2 is still 2. Well, reading the original problem as though it were a sentence, which indeed it is in mathematics, this says 5 times some number is negative 15. Of course, we could have told just by looking at this from memory. 5 times negative 3 is negative 15. So the answer really is not the problem. The problem is the process we're using so that we can use the same process when the answer is not so obvious, but the procedures are the same. The point is, this is telling us what 5 times the number m is. We don't want to know what 5 times the number is. We want to know what 1 times the number is. So if you think, I don't want a 5 times, I want a 1 times, and you think, since I have a 5 times there, and if you recall the cancellation law, it suddenly dawns on us that because that's multiplication, if I had a fraction, which is another way of saying division, and if the fraction had a 5 on the bottom, I could divide top and bottom by the 5, and that would give me 1 times the m, which is what I want. So really, it's not isolating the m, that's logically the procedure, it's that I want 1 times an m. It's just that 1 times an m, of course, is the same thing as just an m. But then if I divide one side of an equation by anything, the division law of equality says I must divide the other side of the equation by the same amount, and hence we have our procedure. Now again, one might say, well, gee, since I can just see that 5 times negative 3 will give me negative 15, why don't I just write the answer down? And of course, that is the case. If you just see the results, quit, you're done. The reason we want to focus on procedure is because of this. In more advanced application, you seldom get simple numbers and simple coefficients. They're somewhat messy. And it's not quite so obvious what number, called r here, I can multiply by negative 29.3 and get negative 228.54. But the procedure still holds. I have this number times my variable, and I would like for that to be 1 times the variable. Now, thinking in terms of that cancellation law, I realize because I have multiplication, that's what brings in the cancellation law, if I had this same number in the denominator, then this would divide into itself once. We call that canceling out in shorthand slang. But then because I divided this side by negative 29.3, I must divide this side by negative 29.3, and that will give me on this side the 1 times r I want. Then finishing the arithmetic on this side gives me my answer. And of course a negative divided by a negative is positive, and of course with decimals this messy we would use a calculator. So 228.54 divided by 29.3 equals 7.8. Now while we're at it, let's show that our calculator could divide with the negative numbers themselves. I could say 228.54, that's a positive number, push the change sign key, which makes it negative, divide. Now 29.3, that's positive, I want negative, change sign, equal, and it does come out positive 7.8. But this is a nice point to realize that I can do this faster in my head than on the calculator. So calculator does not always save you time. With sign numbers, frequently it's easier to work out the signs mentally than work with the absolute values on the calculator. But you see how that cancellation law allowed us another way of looking at this procedure? It's true. Division undid multiplication. Then I must divide both sides by the same thing. But it's not really an r I'm isolating. An r verbally is the same thing as mathematically as saying 1 times r. So it's that 1 times that I'm trying to get on one side of my equation, then the other side provides what we've been loosely calling answer. By looking at the problem that way, you can avoid this common error of many students. Many students at this stage would say, hey, they want to solve for a. See, I've isolated the a, and the answer is 15.7. they fail to notice that you have not isolated an A. You've got this thing still here, this opposite sign. Note, I didn't say negative, I said opposite. And it's not the opposite of A that we want to solve for something. It is 1 times something. And the opposite of something is not the same thing as 1 times it. In fact, specifically, recall from a lesson ago that the opposite of something can be thought of as negative 1 times the m in this case. So the opposite of A means negative 1 times A. And I don't want negative 1 times A. Solving an equation means to get it in the form of 1 times A, which we normally write this way. So I don't want this negative 1 times here. I want positive 1 times. Well, in this case, I can simply remember that a negative 1 times negative 1 is positive 1. And since I multiplied this side of the equation by negative 1, the multiplication law of equality says I must multiply the other side by the same amount, which of course would give me a negative times a positive, or negative 15.7. So my answer is not 15.7, but negative 15.7. Now, realizing this, just right up here, you will learn to say that negative 1 times the opposite of A is A. But then I have to multiply the other side by negative 1, which gives me negative 15.7. And then, of course, with very little practice, you're simply doing this whole thing mentally, which is what we want in the end. But see, always remember it's a positive 1 times the variable that I need in order to say that I've solved the equation. That way of approaching the problem makes a problem like this rather easy, rather than as messy as it might first seem. Note what we really have here is a negative 7/8 times y. What I want is 1 times y, not this times y. So we ask ourselves, what could I do to somehow miraculously make this to suddenly become 1 in one full move? Can you see it? Well, if you recall from arithmetic, the reciprocal law, which says any fraction, positive or negative, times its reciprocal is always 1, and that's the coefficient I want. Can you see that this is really a special case of the cancellation law? These all go into each themselves 1 time. So with that at the back of my mind, I think, gee, if I were multiplying this whole expression by the reciprocal, which is negative 8/7, then any number times its reciprocal is the 1 times y I'm after. But the multiplication property of equalities says if I multiply this side by anything, negative 8/7, that's fine. You just be sure to multiply the other side by the same amount. Now we can see that a negative times a negative is positive, and we can use our cancellation law, and the answer is no, we can't. There's nothing to cancel here. So negative times negative was a positive. 4 times 8 is 32 over 7 times that, and I'm done. So keep in mind it's 1 times that I want, and never forget that reciprocal law. That's extremely valuable at times. Now, returning to the basic presentation of this particular lesson, which was simply to remember that a negative into negative is positive, and of course 3, and a positive into negative is negative, and of course 3 in this case, and a negative into positive is negative 3. Or we stated that the rules for division in algebra are the same as sign-wise as multiplication. When dividing or multiplying like signs, you have positive. When dividing or multiplying unlike signs, you have negative. Let's conclude just by showing that by looking at this 2 somewhat differently, it begins to make a bit of sense too. This division, after all, is also a fraction, and I can always multiply top and bottom of any fraction by any number I choose. So I could choose negative 1. And of course, negative 1 times that is 18, and negative 1 times that is 6, and 18 divided by 6 is patently positive 3. We've known that all along. Same thing down here. If I were to multiply top and bottom by negative 1, I would get positive 24 divided by negative 8, which is the same as the problem down here. So that tells me that however the signs are, the results still come out to be negative. See how extremely valuable it is sometimes to look at the same problem from a different angle. This will be much of your algebra when you get into it properly. It simply becomes the art of always looking at a problem from 2 or 3 different angles. And once again, when you're solving an equation, note that we ask what's the number doing to the variable. It's multiplying. Well, I want not that times r, but 1 times r. Then recall from the reciprocal law that any reciprocal times the fraction is 1. The multiplication property of equality says, fine, multiply both sides by the same thing. And then a negative times a positive is negative. Using the cancellation law, and we can make what seems to be messy problems at the start to in fact be rather simple. I did this rather rapidly just to try to emphasize that after completing a homework assignment, you should have done enough problems that even though you start slow, you will conclude by going just this fast. Try it and see if it works. Our next lesson will mix these 4 operations together. So until then, this is your host, Bob Fennell.